In classical mechanics, an impenetrable boundary acts as an absolute wall. When a physical particle collides with a boundary it simply cannot cross, it rigidly reverses direction and bounces back. The infinite square well operates on this exact idealized assumption. But real physical systems, from semiconductor junctions to atomic nuclei, have finite barriers. The classical physics assumption for a finite barrier is straightforward. If a particle's total energy is less than the barrier height, it remains permanently trapped. But quantum mechanics presents a completely different reality. The Schrödinger equation dictates that the wave function does not immediately drop to zero the moment it encounters one of these classical boundaries. These are exact eigenstates for a particle in a finite well. The upper panel shows a tightly bound state locked inside the dashed boundaries, but penetration depth depends on energy. The loosely bound state below leaks deep into the classically forbidden region. This wave function leakage across boundaries is a direct consequence of the wave equation. It is the mathematical mechanism underlying quantum tunneling. You will often hear a heuristic taught in introductory courses claiming that particles borrow energy to hop over a barrier. That explanation relies on the time-energy uncertainty principle, and it is a mathematical misinterpretation of the Schrödinger equation. In an energy eigenstate, a particle's total energy is strictly constant. It remains strictly less than the barrier height at all times. Because the energy cannot spontaneously spike to clear the wall, the physical mechanism for crossing the barrier must be found in the mathematics of the state itself. To calculate tunneling accurately, we have to abandon classical energy jumping intuition and rely exclusively on the strict boundary conditions of the wave equation. To see exactly how those boundary conditions work, we set up a theoretical model with a continuous stream of quantum particles approaching a barrier from one side. A rectangular barrier rises to a fixed height, V0, from a flat baseline. The total energy, E, is a horizontal dashed line permanently below the barrier's top. We divide this space into 3 mathematical regions to solve the Schrödinger equation. We start by solving the equation in region 1, where the incident wave approaches the barrier and the particle's total energy is greater than the potential energy. In this region, the positive kinetic energy term forces the second spatial derivative in the differential equation to be negative. This dictates that the mathematical solution is an oscillating wave. In the free space before the barrier, the mathematics dictate that the particle behaves exactly as intuition expects. It propagates as a normal oscillating matter wave. The analytical focus now shifts to region 2, representing the interior of the classically forbidden barrier. Here, the barrier height, V0, is strictly greater than the total energy, E. As a result, the kinetic energy drops below zero, forcing the differential equation to flip its sign, yielding a positive second derivative. A positive second derivative means the wave function curves away from the axis. It cannot mathematically produce an oscillating sine or cosine wave. The only valid mathematical solution for this specific differential equation is a sum of real exponentials. And since the wave cannot grow to infinity, it must take the form of a decaying exponential. In physics, we call this non-oscillating decaying solution an evanescent wave. The Schrödinger equation requires the wave function to be perfectly continuous everywhere. The oscillating wave from region 1 must splice seamlessly into the decaying exponential in region 2. The wave function does not hit a wall and stop. Strict rules of differential continuity force it to splice directly into this decaying evanescent state. The physical reality is that the barrier has a finite width. It ends before the exponential wave can decay entirely to zero. It hits the second boundary, holding a small positive amplitude. Crossing into region 3, the potential drops back to zero. The total energy is once again greater than the potential energy. The differential equation flips back to its original state, demanding an oscillatory solution once again. The final boundary match requires the decaying wave to splice back into a sine wave. But because of the decay across region 2, this new oscillation is locked at a severely reduced amplitude. Born's rule states that the squared modulus of the wave function gives the probability density. That final reduced amplitude dictates the exact probability of transmission. Tunneling is determined entirely by the continuity of the wave function and the finite width of the barrier. The particle crosses without violating energy conservation. Across this geometry, the wave function changes character, from oscillatory to evanescent and back to oscillatory. At no point did the particle borrow energy. Classical laws of energy conservation were never suspended. Experimental data covering alpha decay to scanning tunneling microscopes perfectly matches the transmission coefficients derived through this exact boundary matching method. You will apply this logic and compute these exact transmission coefficients yourself in the end of chapter problems. In the quantum world, human intuition fails. Rigorous adherence to differential equations and boundary conditions is the only reliable path to physical truth.